All right, let's look at the design process for a cam and follower. And as we mentioned earlier, timing is the main element. So what we do first is we decide how we want this follower to move up and down. Now I'm going to expand this slide screen. Once we decide how we want the follower to move, we graph that motion, and the graph is called a displacement diagram. Here's one at the bottom. And then we'll use that displacement diagram to draw the lumps on our cam. And in the next set of slides after this one, we'll look at how to do that. So displacement is just the difference between the starting point and the ending point. This happens to be a piston and crank, and here is I drew this displacement diagram for this piston and crank. And this displacement diagram is a graph of what the follower is going to do, going up and down as the cam rotates. Here's a displacement diagram, and you'll see the displacement, the up and down thing, on the vertical direction, and along the horizontal axis is the degrees of rotation. So in our diagram, we graph one full revolution, 360 degrees. Then we divide the up and down motion into sections, those are called periods, and one period might be when the follower rises. Here's one, here's another one where it rises, that's called rise, and here's another period where the follower falls, that's called fall. Sometimes you want the follower not to go up or down, you want it to just stay at one height, and that is called dwell. We saw that in that animation we were looking at. In the displacement diagram, in this graph, because the follower is not going up or down, dwell looks like a horizontal line. So here in this graph, follower is going up, then here it dwells, so it's just sitting in one spot. Then follower goes up, then it's sitting in one spot. Then follower comes down, then it's sitting in one spot. So each of those places where there is dwell, you'll see a horizontal line in the graph. You draw the height of your displacement diagram to scale. So in this example, displacement was 1.5 inches, total rise and fall, so that's how high they drew their graph. The one we're going to draw happens to have a displacement of 3 inches, so we'll draw our graph 3 inches high. The length really doesn't matter. We are going to draw our displacement diagram 12 inches long, just to be consistent, but when you're designing stuff, you could make it any other length that you want to. Whatever length you make it, then you're going to divide it up into degrees. This length is 360 degrees, so you'll just start splitting it up. Anytime you have a rise or a fall, you need to divide it into 6 equal parts. And that's the minimum. You could divide it into more increments if you wanted to, and the more fine divisions you make, the more precise it will be, but you need at least 6. So if you have 60 degrees of rise, each one of those lines will be 10 degrees. If you had 180 degrees of rise, each one of those lines would be 30 degrees, and so forth. Then you think about what type of motion do you want, and the ones that we are going to use in our assignment are the second one, modified constant velocity, and the last one, harmonic. But let's just cruise through all of these so we can get a sense of what they are. Constant velocity, the graph is just a straight line, and it's where the thing just goes straight up a certain speed with no speeding up or slowing down, or straight down a certain speed. That's great while it's in the middle of its stroke, but you get clunking at the beginning and the end. There's a very abrupt edge. So we don't usually want constant velocity. We want modified constant velocity. And this is what you'll do in your displacement diagram. We want to put a curve at the beginning and a curve at the end. It's kind of like a freeway on-ramp and off-ramp, where our follower can slow down as it eases into the next period. Uniform accelerated, constant velocity has a uniform speed. Uniform accelerated has a uniform acceleration, and it's more complicated to lay out, and we won't do one of those. Even more complicated to lay out, but the very best shape, is called cycloidal. This is the smoothest follower motion. There are no abrupt changes in speed or acceleration. You can run machinery at a high speed with cycloidal motion. And a cycloid is what you would get if you went out at night and you had someone tape a flashlight to the rim of a bicycle wheel, and then you had them walk along the sidewalk, and if you stood on the side and you watched that thing in the dark, you would see that flashlight path as the bicycle wheel turns and the bicycle goes down the sidewalk. That flashlight would trace a cycloidal path. Well, a few years ago, this photograph was on the cover of the local newspaper. It was the path traced by a rare miniature tornado, a cyclone that went through the Willamette Valley, and this is the path that it traced in a newly plowed field, newly disked and harrowed field. And you can see the clear mark of a cycloid. What we are going to draw in our assignment is a thing called harmonic motion, and it uses a sine curve. And if you have not run into a sine before, well, you probably have run into a sine before, and you are probably aware that a sine wave is just a graph of a spinning circle. And you find a sine wave all over the place in nature, graphing lengths of days as the earth turns through the seasons. In a power plant, the sine wave is the shape of the current and voltage as the generator spins in a circle. You just see these all over the place. And they're relatively smooth if you're thinking about a follower. And in a separate slide, we'll look at how actually to lay these out. But the basic idea is, so here's a displacement diagram that's 3 inches high. And let's say you want a sine curve both rising and falling. You put half a circle on the end of your graph. However big the graph is, that's how big you make your circle. And you divide that half circle into 6 wedges. And what is that? Let's see. This is 180 degrees of circle, and so these must each be 30 degrees of angle. Then, where the end of one of those arms hits the circle, project a line over into your displacement diagram, and project a line over from each point, from each line on your half circle. And then where those lines intersect your vertical lines, which represent degrees, make a point and connect the dots. So here's 30 degrees. Well, let me do it in picture 4. This first line is 30 degrees. There's where it intersects the 30-degree mark. The second line is 60 degrees. There's where it intersects the 60-degree mark, and so forth. In our assignment, which we'll look at in a separate video, In our assignment, it says we're going to make a displacement diagram, and we want the follower to do this. We want it to rise for 3 inches. Okay, it's going to rise for 3 inches and later fall for 3 inches, so we'll make our graph 3 inches high. It'll rise in modified constant velocity motion over a stretch of 180 degrees. And we'll modify it to 1/3 the displacement. What does that mean? Okay, the total displacement is 3 inches high. 1/3 of 3 inches is 1 inch, so we're going to draw a circle with a radius of 1 inch. I'm going to show you that in the next slide. Don't worry. So it's going to rise for 180 degrees, then it will dwell for 30 degrees, then it will fall for 120 degrees in simple harmonic motion. That means one of those half circles, and then it will dwell from there to the end of the cycle. And we're going to make our displacement diagram 12 inches long. So here's the start of the thing. It's going to rise in modified constant velocity for 180 degrees. So the first half of your graph will go from 0 degrees to 180 degrees, and that degrees means that's how far your cam has rotated. It's rotated a half a circle so far. And you're going to modify it, so instead of a straight line, you'll start with an arc at the bottom, and it'll have a radius of 1 inch. There it is. You'll have an arc at the top. It'll have a radius of 1 inch. And then you'll connect those two arcs with a straight line going tangent, tangent. So that was the first half of your graph. Then it will dwell for 30 degrees, so you'll have a straight line across the top from 180 to 210. And then it will fall over 120 degrees. And by the way, I squished the proportions of this graph so I could fit it onto the slide. If this is 3 inches high, this is not 12 inches long, so you can see that the proportions are not exactly the same aspect ratio you will have in your graph. Sorry about that. So anyway, it will dwell from 180 to 210, and then it'll fall from 210, 120 degrees to 330. Then it will dwell for 30 degrees to the end. Here is the half circle at the end of the graph where you can project lines over from the circle into this place where your sine wave is going to go. And then here is approximately what your graph will look like. As I say, I squished this so it's narrower in order to fit it onto a PowerPoint slide. Yours will look a little bit more stretched out than this. And so here in the beginning is the radius 1 inch and the radius 1 inch for the modified constant velocity. Here's 30 degrees of dwell. Here's 120 degrees of harmonic motion. And notice how in the first 180 degrees, I've divided this section into 6 segments. Then notice in the fall, from 210 to 330, I divided this into 6 segments. 6 segments, those segments are shorter than the 6 segments in the first half. First half I went every 30 degrees. In the fall I went every 20 degrees. And then dwell for 30 degrees at the end.